great pleasure to be here. Let me start. This is actually an ongoing work that I'm going to report, and this is all the people who have taken part in various parts. So it will eventually maybe split into certain subsets, publishing various results, but all these people have contributed. Actually, I don't like outline is not needed. So let me define what homomorphism is. It's between two graphs is a map from one graph into the other, which preserves adjacency. So, for example, you can map this pentagon onto the triangle, as the arrows indicate. Let me point out here right away that if I color the vertices of the triangle, then I can pull back this coloring to the pentagon. And in fact, this will be exactly a good coloring of the pentagon, because if you take any two adjacent points, they are necessarily mapped onto adjacent and therefore different points of the triangle, and so they have different colors. So coloring problems are hidden here. Let's look at another example. This time, this is the target graph, this little graph, and I will allow loops mostly in the target graph. So let's allow a loop in the target graph. So if I map this pentagon into this target graph, then the only conditions are, since here the only missing edge is that this black node is not connected to itself, so I'm not allowed to map two adjacent nodes on the black node. I can map anything on the white node. So in other words, such a map will be determined by the set of those nodes which are mapped onto the black node, and they must form an independent set. So maps into this graph sort of naturally correspond to independent sets in the graph, and those correspond to colorings. I will denote by hom GH the number of homomorphisms of G into H. So by the remarks I made before, the hom G into a complete graph on Q nodes is with the number of Q colorings of G. Because the maps are in one-to-one correspondence with these Q colorings. And similarly, hom of G into this graph with this little loop is equal to the number of independent sets in G. Or we can sort of turn things around and look at like hom of K3 into G. And this is the number of triangles of G, at least as long as we assume that G has no loops. Because if G has no loops, then to map K3 into G, we necessarily have to map it in a one-to-one way. So we are counting. Triangles were labeled triangles, of course. So actually, every triangle of G gives rise to 6 possible maps. But Now, there's also a weighted version which I'll need, and that looks a little hairy. But so I have a graph, the target graph H, as a certain set of vertices, edges, and there is a weighting of the vertices and the weighting of the edges. I will assume that the node weights are positive or non-negative, but the 0 will not play any role. We could just delete those nodes. But I'm not assuming this necessarily about the edge weights. And then we can define hom of GH as summations over all maps from VG into VH. And then for every such map, I just take the product of the weights of the images over every node of G, and then similarly take the product of the weights of the images over every edge of G. And of course, the special case when all the alphas and betas are 1, then this is just 1. Well, this is a 1 provided, okay, so here in beta, if the two indices are not adjacent, then I consider beta to be 0. So therefore, every map which maps some edge of G onto some non-edge, so some edge of G is mapped onto some non-edge, would get a 0 weight. But if all the others betas are positive, so then say equal to 1, then this is just counts 1 for every homomorphism. So this is generalization. Okay. This function hom G H satisfies some simple properties. If you take the disjoint union of two graphs, then you can, of course, independently map them into H. So the number of homomorphisms is just multiplied. If G is connected, then mapping G into, so now what happens if H is the union of two connected pieces? Well, if G is connected, then the number of homomorphisms of G into this union is, well, every homomorphism either goes into H1 and H2, so you get that the number of homomorphisms just end up. So this sort of tells you that if you know how to count homomorphisms between connected graphs, then first you can extend it to disconnected H using this, and then you can extend it to disconnected G using that. And there's also another rule which we'll need later, maybe tomorrow, is that if you take the Cartesian product of two graphs, well, that's our direct product of two graphs, then there is this, again, multiplicative rule. For this, the product is defined, I think it's best defined by this picture. So here is one graph, here's another graph. So you take the Cartesian product of the underlying sets, and every edge here and every edge here gives rise to two edges. So in other words, you connect 2 points here if their projections here are connected and their projections here are connected. So in particular, this node is connected to itself because its projection here is connected to itself and its projection here is connected to itself. So with this definition of the product, there is this rule. It's not hard. These are all very easy to verify. Now, here is well, sort of a very old observation, but very useful, that if you have two graphs, G1 and G2, so that for every f, every f has the same number of homomorphisms into G1 and G2, then they are the same graph for, isomorphic graphs. I'll come back to how to prove this because it's easy, but let me first show that this actually has some interesting implications about the direct product. So, for example, if you take the direct product of G1 cross G0 and G2 cross G0, and you know that they are isomorphic, and then you have to make an additional assumption that G0 has a loop, then you can cancel G0 and it follows that G1 is isomorphic to G2. And if you take this sort of the square of G1 with respect to this direct product, and it's isomorphic to the square of G2 with respect to this direct product, then again, it follows that G1 is isomorphic to G2. This is a very easy application of this above fact, because I'll show how does this second line follow. So you can sort of take square roots with respect to this direct product. So why is that? Well, this assumption implies that for every f, if you count homomorphisms of f into G1 cross G2 is equal to the same with G2. But this number is just the square of the number of homomorphisms of f into G1 and G2. So you can take square root. These are just numbers, positive numbers. And, of course, then now you have to appeal to this lemma that holds for every f, so it follows that G1 is isomorphic to G2. Yeah. In the first one, the proof is very analogous, and G0 must have a loop. Well, if it doesn't have a loop, then this number that you want to divide with could be 0, and that's why such an assumption is needed. It can be relaxed, but something like that is needed. Anyway, so I just wanted to illustrate that these homomorphisms functions are sort of interesting. But let me come to why. Okay, so from a combinatorial graph theoretic point of view, it's probably more natural to count subgraphs instead of homomorphisms. So count the number of copies of G in H as a subgraph. Say labeled copies again. So if the triangle really gives rise to 6 labeled copies of the triangle in G. And you could be also interested in counting the number of induced subgraphs, induced copies of G in H. That means that copies of G in H where between the points that are images, there are exactly those edges in H which are in G. But these are actually not very different in the sense that, first of all, if you know induced copies, then I probably have here a reverse inclusion. But anyway, so if you want to count the number of how many copies of G is in H, and you know how to count induced copies, then of course, if you have a copy of G in H, then the only reason why this is not an induced copy is that there may be more edges there. So you could, so if you sum the number of count the number of induced copies for all supergraphs of G, you get this, and then you can just do Möbius inversion and similarly count. If you know how to count non-induced copies, then it gives you how to count induced copies. And there is a similar situation that if you know how to count copies of G, then you can count homomorphisms of G, because you can realize every map by first collapsing the points that you have to collapse and then map whatever you get. So I didn't write it out formally, but so in G you collapse some partition into one point, and then you map the resulting graph into H. And then, of course, again, you can do a Möbius inversion. Here it will be a little bit more complicated. The coefficients will be not just plus minus 1, but there are some Möbius function there that you can write there. So if you know how to count homomorphisms, then you also tells you how to count subgraphs. As a special case, I will refer to this a bit later. If you want to count, for example, the number of subgraphs, number of labeled subgraphs of H, which are 4 cycles, then you can look at all maps of the 4 cycle into H. But now you overcounted because you have to subtract those where 2 of the points coincide. So either these 2 coincide or those 2 coincide. In both cases, you get this graph. So you get twice the number of homomorphisms of this graph into H. But now you have to correct because some things you've subtracted twice. Now, let me remark that this formula here immediately proves this fact here. because if G1 and G2 so every F has the same number of homomorphisms of G1 into G1S in G2, then by this inclusion-exclusion formula, you get that the number of subgraphs, number of embeddings of F into G1 is the same as the number of embeddings of F into G2 for every F. So in particular, for F equals G1, this is positive, so this is positive, so G1 embeds into G2, and then similarly G2 embeds into G1, so they must be the same. Okay. Now, it turns out that we get a little bit. So it's really not that interesting because these functions uniquely determine the graph. So you get something more interesting if you normalize these functions. So let TFG denote the following. I count the number of homomorphisms of F into G, and then I divide it by the size of G to the number of nodes of G to the number of nodes of F. So another way of saying this is that I pick a random mapping of VF into VG, and then this expresses the probability that it's a homomorphism. So it's a number between 0 and 1. Let script G denote the set of all finite graphs up to isomorphism. And now let's look at the following set. Now this is a little bit. So what I want is the following. To every G, for every graph G, I look at these numbers T, F, G, and I let F go through all finite graphs. So without the normalization, this would uniquely determine G. But now we normalize, so it doesn't uniquely determine G. For example, it's easy to see that if I just blow up vertices of G into parallel vertices or twin vertices, then I just get the same number. So this does not uniquely determine G. And so to every G, I get this infinite vector, which has a coordinate for every F. And then I look at the set of all these vectors, and that's a set, that's a countable set in R infinity, and then I take the closure of that. Now the closure, I just take pointwise closure, so coordinate-wise, coordinate by coordinate. So this gives me a set T, and I am interested in properties of this set. Now, why am I interested in properties of this set? We'll see. I hope I can convince you that it's an interesting set, that if you understand the structure of this set, you will understand a lot about graph theory. One thing that this suggests is to define convergence. So we can say that let Gn be a sequence of graphs. Normally they would be bigger, and so the size would tend to infinity. And I say that this sequence converges to a graph G if for every F, TFGN tends to TFG. Now, I will read this out, this TFGN, as the density of F in Gn. So it means that a random map, what's the probability that a random map will, okay, so that was the definition. What's the probability that a random map is a homomorphism? That sort of essentially means what's the density of F in Gn. And so the density of F in Gn tends to the density of F in G. And more generally, we can say that a sequence of graphs is convergent, and there will be a right convergence. So at the moment, so later on I will have to refer to this as left convergent. If for every f, the density of f in Gn tends to some number which depends only on f. And we'll see that there are interesting examples of these kind of left convergent sequences. Now, let's, well, this is now really not exactly what I had before. We had this for the home function, but it's easy to see that it also holds after normalization. So there is this, if you take, and that means disjoint union of two graphs, and this density is just the product of the two densities. Now, what does it mean? So this is now about this set T, and maybe I should just, okay, so it's difficult to draw in infinite dimension, but so there's somewhere this set T. This was the set of all these limit points. So to every graph G, we associated a vector. The coordinates of the vector told us what's the density of this subgraph and that subgraph and that subgraph and so on. And then we sort of looked at these points and their limit points. So it's a closed set. And then the first question is, how rich is this set? How thick is this set? And one of the ways, so this first line says that certain coordinates of this f, of this vector, are determined by other coordinates. If a coordinate corresponds to a disconnected graph, if a graph is disconnected, then it can be written as the union of two disjoint graphs, and it's determined by two other coordinates. So it's some kind of algebraic surface that contains this whole T. So really we can sort of throw out the disconnected coordinates. They don't give any new information. So now let's look at connected graphs. So here is a result which says that basically these relations are all the equations that you can have. So the way to formulate it is that I look at any finite number of coordinates, finite set of coordinates, and then now we have thrown out disconnected graphs. So they are coordinates which correspond to disconnected graphs. So we only look at frequencies or densities of connected graphs. And then now this will be, if I pick a finite set of coordinates, so this will now be a set in a finite dimensional space. And we proved with Joel and Paul Erdős many years ago that this set actually is full dimensional. So it has an interior point, which says that really there is nothing, no other equation besides this. So, but that's fine, but are there inequalities? And now you begin to look around and you find that there are many interesting inequalities which correspond to various simple facts about graph theory. So, for example, Turan's theorem for triangles, actually this is a strengthening of it, I think, due to Goodman, says that if I look at the density of triangles in a graph, then this is greater than or equal to the density of edges times 2 density of edges minus 1. And here as you see, I suppressed the G here, so there should be a G here. But in fact, this is not only true for a particular G, but then they also hold for the closure. So this T is just a point in this, an arbitrary point in this, because any such inequality holds for the closure, of course. So you see that it says is that if the edge density is larger than a half, then there must be a triangle, so it's positive. And I mean, similarly, the whole Turan's theorem, I mean, for any complete graph could be formulated by a similar inequality. The Kruskal-Katona theorem specialized again, looking at a special case. If you, it tells you that, so Turan's theorem tells you what's the minimum number of triangles given the number of edges. The Kruskal-Katona theorem tells you what's the maximum number of triangles given the number of edges. And it has this nice form that the number of triangles is bounded by number of edges to the 3/2. Now, actually, I should say this is an asymptotic version of it. The Kruskal-Katona theorem gives some very precise inequality for any fixed number. And this is just the sort of the asymptotic version of it. But this is an inequality which is, again, valid for if I put any graph here, G and G here. So it's, again, valid for this limit set. Actually, okay. Or here is another classical theorem. Erdős is one of the earliest theorems in extremal graph theory. Is Erdős's theorem, which says that if a graph with n to the 3/2 graph with n to 3/2 edges contains a quadrilateral. I claim that it follows from these two inequalities. The density of these path of length 2 is greater than or equal to the square of the edge density, and the density of 4 cycles is greater than or equal to the square of the density of the path of length 3. Actually, let me sketch the proof of that. So, first of all, so the assumption is that the number of edges is n to the 3/2, actually, it's a 2. So the edge density is greater than or equal to the square root of 2 over n. So the density of these guys by the first inequality is greater than or equal to 2 over n. And this is an identity we already had, that how to count. Now, okay, so we apply this again, and you get a lower bound on this, on the density of these. But of course, we are not interested in the number of homomorphisms of this into the graph. We are interested in the number of, we are actually to show that there is a 4 cycle, not just that there is a homomorphism of, that's trivial, that the 4 cycle can be mapped into any graph. Just, go back and forth twice on an edge. We want to show that the 4 cycle can be mapped in a one-to-one way into a graph, if this holds. So we have to look at this inclusion-exclusion formula for the, now this is the number of one-to-one maps of the 4 cycle into the graph. And that's, and the only difference is that I have this n, which is the number of nodes. Appropriate powers of n has to, because I'm not, this is the home. And t is divided by, was divided by n. Now I can estimate this from below by this second inequality. And so I get this formula. And I just rewrite this and notice that this expression here in the brackets is positive because of this inequality. So everything here is positive. So there is a 4 cycle. Now, this is not really a new proof, and I haven't proved you these two inequalities either, but it certainly shows that there is some sort of a calculus of these small homomorphism numbers, which might be useful. But actually, we'll see that it gives much more. Let me maybe take a minute, which I haven't, and draw you a picture. So this is the T of edge versus T of triangles. So this is the projection of this big set T on just these two coordinates. And let's see what is the information that we know about this. Well, we see here two theorems. One is this Turan-Goodman theorem, which gives actually a parabola like this. And we know that the number of triangles is above this. The other one is the Kraskal-Katona theorem, which gives here some other curve, and the number of triangles is below this. And so the question is that all we know? Well, as it turns out, there are infinitely many points. The upper edge is fine, but on the lower edge is more complicated. There are infinitely many points. So at 1/2, get 0 at 2/3, you get the right value from that if you take a graph, this Turan graph with 3 classes that has exactly the right density there. And then at 3/4, again, you get the right value, and so on. There's an infinite number of points. And you would think that in between, it's maybe you don't get exactly on this curve, but you can get arbitrarily close. But it turns out that that's not the case. In fact, Lovasz showed that the truth is above the chord. So there's a convex curve, but in between it turns concave. And in fact, there is an explicit conjecture which tells you that there are certain, I think these are cubic curves, that would describe this. And Miki Simonovic and I have a theorem which shows that this is indeed true in a small neighborhood of each of these points. And there's some technical difficulty to extend it. So I think with maybe, writing a 200-page long paper, one could probably do that. But it would be much nicer to get it by some more elegant argument. But anyway, already if you look at just these two coordinates, there's a large variety of graph theoretic problems and information which is expressed in the projection of this set T. So the question is, there is all these huge number of inequalities, all corresponding to every possible theorem in extremal graph theory. So is there any hope to get some kind of sort of common view on those? And I will try to propose something. But before that, let's look at another word in the title, the quasi-random graphs. These are very interesting objects which were introduced by Thomason and Chung, Graham, and Wilson. And so here is the idea. I will not. It's a nice theory. It has lots of non-trivial and interesting results. So I will just try to get as much as I need. So quasi-random graphs are sort of graphs which mimic true random graphs, but they are actual deterministic graphs. And so how do they mimic it? So suppose that we look at first a true random graph to see what we want, and this has n nodes, and every edge is put in with probability p independently of each other. Now, what do we know? It's very easy to compute that if I want to map f into Gn, I randomly map f into Gn, then the probability, now at the moment we have two probabilities here. There is Gn itself is random and the map is random. But if both of them are random, then certainly the probability that this map is a homomorphism is this p to the number of edges, because every edge independently has to satisfy this condition. At least if n is very large, so that I don't have to worry about two edges falling onto the same thing. And then it's easy to see that actually this is true. This relation is true. So it's some simple law of large numbers type argument. So with probability 1, if Gn is this sequence of random graphs, then this density of f has this simple form. And so the definition, or one possible definition of a quasi-random graph, actually, to be precise, we have to look at a sequence of graphs increasing in size. So this sequence is quasi-random if it satisfies this condition, so that for every f, every fixed f, the density of f in Gn tends to this value. And I'm sorry, there's no with probability 1 here. That's exactly, okay, sorry. That's a mistake. So this is a deterministic fact. There is no probability here. So the interesting thing about this is that there are quasi-random graphs, very nice ones. Oh, before that, let me mention this, that in terms of our notion of convergence, quasi-random can be expressed simply that Gn tends to this graph, which is a single point with a loop, and the loop has weight p. Because this graph will have these numbers, and so it's just a convergence. Anyway, so here is a nice example of quasi-random graphs, Paley graphs. So a Paley graph is defined on a prime number of nodes, and the prime has to be congruent to 1 mod 4. And the nodes are labeled by 1 through p minus 1. And I and j form an edge if and only if the difference is a quadratic residue, a square. So here is the simplest example of a Paley graph for p equals 5. Now, why are these graphs quasi-random? Note that the fact that these are quasi-random doesn't seem to contain a lot of non-trivial number theory. So, for example, if they are quasi-random, then the number of complete graphs on 5 nodes in them should be whatever it is. Now, what does it mean? It means that the number of 5 tuples of numbers, so that the difference of any 2 is a quadratic residue, is whatever this number should be. And well, this looks like a non-trivial number theoretic fact. So it seems that to prove this, well, you can actually go through these and use number theory. But it turns out that there is a very beautiful theorem that makes this argument very easy. And so here is the theorem of Chung, Graham, and Wilson. It says that to check that Gn is quasi-random, it suffices to check that for a single edge, it tends to some p, the density of the edge density tends to some value p, and the density of 4 cycles tends to p to the 4th. So in other words, out of these infinitely many conditions, that for every f, the density of f's has to be p to the, so ef, so it's to tend to the appropriate value, it is enough to require that 2 special graphs, the edge and the 4th cycle, satisfies this. It's a very surprising theorem. And so I'll try to sketch you how it relates to these things that I have introduced so far. So let me start with saying that actually I can sort of forget about this sequence Gn and about convergence, and I could go right away to the limit, and I could just take, so it's enough to prove that if I take a t in the limit set, it's a vector, so it has a coordinate corresponding to every graph. And if the coordinate corresponding to an edge is p, and the corresponding coordinate corresponding to the fourth cycle is p to the fourth, then for every f, necessarily the coordinate is equal to p to the size of the number of edges of f. So it's easy to see that this is really equivalent to that. But it's an easier way to think about it, because now there are no error terms, and I don't have to worry about anything like that. So let me try to so I will try to sketch you how to prove this, but first I need some preparation. And this is really, now I have come to the main object that I would like to talk about. So this thing will come up tomorrow as well. So first I have to define what a k-labeled graph is. A k-labeled graph has k nodes labeled 1 through k. And I denote by gk the set of all k-labeled graphs. I'm a bit sloppy here, so it's a representative for each isomorphism class of these graphs. Now, I need an operation which I will denote simply by just like multiplying them. If f1 and f2 are two such k-labeled graphs, then I take the union, but now not the disjoint union, the labeled nodes I identify. So I glue them together along a set of size k. These. Now, okay, so this is it, and now comes this object that I would really use a lot, and this is what I call the connection matrix. So fix any graph G and any number k. And this will be a matrix indexed by these k-labeled graphs. So it's a graph where the rows and columns are both indexed by these k-labeled graphs. It's a matrix. And it will be a symmetric matrix. And if I take two k-labeled graphs f1 and f2, then the entry in the f1, f2 position will be the density of this glued together copy in G. I don't know if this helps, but it looks a small. Okay, so this is an infinite matrix. I mean, it says, so this is a tiny part of it. For k equals 2, so here are all graphs listed, and I mean I didn't write out the labels. So if there's, they all have 2 points, 2 dark points, and the upper one is 1, 0.1, 0.2. And okay, so it goes on and on. And so, and you notice I allow multiple edges that will be, that doesn't really matter if I count homomorphisms into a graph, because if I take if one edge already has a right image, then the other one doesn't give any extra information. But it will be, but it makes a difference if we look at labeled graphs, and it will be convenient. So anyway, so this is now at the matrix of graphs, and I get the numerical matrix by counting how many homomorphisms of this guy has into G, or this guy has into G, or this guy has into G, and so on. And that's the corresponding entry. So the main fact about this is that this matrix even has 2 important properties. First of all, it's a positive semi-definite matrix for every G and every K. And moreover, even though it's an infinite matrix, it has finite rank. And the rank of it is bounded by the number of nodes in G to the K. So this is really a basic lemma, and I will show you the proof is very simple. By the way, this there are some physicists on the list, and they call this first property reflection positivity. So that's apparently, I mean, it's not exactly formulated like this, but that's sort of a version of some principle in physics called reflection positivity. But anyway, let's see the proof. So here is the quadratic form corresponding to this matrix, where, of course, for this to make sense, say this X is a vector indexed by these k-labeled graphs, but there is only a finite number of non-zero coordinates. It's a finite support. Actually, I shouldn't have written equality here because in the definition I have t, but that's just a scaling. So it's another x. Sorry, I had to put the scaling factor into f, but I can just move it over there. So this is really essentially the same quadratic forms. I made a mistake by writing equality there. So let's look at this one. I can rewrite this in the following form. So what is this F1 union F2? Is, F1 and F2 glued together along some points. And I want to count homomorphisms of it into G. Well, I can first decide how to map the common points. And that will be some map of the interval. I mean, these are just all integers from 1 to k into G. And then I can map the rest of F1 and the rest of F2, but now there is no condition, so I can map them independently. So anyway, hom phi should denote the number of homomorphisms which extend this particular phi. But as I remarked, these are now mapped independently, so I can count them and just take the product. So I get this expression. And now all I have to do is to interchange summation and see that it's a summation over all these phi. And here I get a linear summation over all f, hom phi fg times xf squared. So I have written this quadratic form as a sum of squares, so it's positive semi-definite. And the number of these squares is the number of such mappings, which is exactly this size of number of vertices of G to the k. Now, of course, it could be that there is another expression with a smaller number of quadratic terms. So this is just an inequality. But for sort of the generic case, it's equation. So for example, if G has no automorphisms, then it's an equality. Okay. Good. Now let's look at what does this lemma give. Let's start with a very tiny little piece of the first such matrix. And so this is positive semi-definite. So this times this is greater than this times this. So we get that the square of the, and again I suppress G because, again, I could go to the limit. So instead of counting homomorphisms into any G, I always have a positive semi-definite matrix. So in the limit I have a positive semi-definite matrix. So I could just take any point t from this, little t from this set, and I get this inequality. It's easy to see that t of a singleton is 1. There's no condition. It says probability 1, it's a homomorphism. So this is 1. So I get this inequality, which I already mentioned before in connection with the 4-cycle problem. Let's look at another next very simple piece of this. For k equals 2, let's look at just this piece. Actually, it's just, I look at, I think these 4 here. Then I get that this times this, so the square of the density of paths of length 3 is bounded by this times this. And again, the density of this is 1. It's easy to see because there's no edge, no condition. And so I get that the density of 4 cycles. So this was the second inequality. So I now proved you the 2 inequalities that I used. But I can look at another piece of this. For example, I can look at just these. I think that's, at these 4. Because it's positive semi-definite, this times this is greater than this times this. And if you write it out, this means that the density of triangles is bounded by, that's just the density of edges times the density of 4 cycles. The density of 4 cycles increases if I delete 2 of the edges. So I get density of edges times density of pairs of edges. It's multiplicative, so this is just the density of the edges cubed. So that's the Kruskal-Katona inequality. Okay, so we got that indeed the positive semi-definiteness of this matrix really contains combinatorial information. Let's now return to the issue of quasi-random graphs. And suppose that T of a single edge is some P. Now, actually, I'm assuming that this is P to the 4th, but we already know that the square of this is less than this, but the square of this is less than or equal to this, so this must be equal to P squared. This is these 2 inequalities I proved in the previous, or maybe 2 slides back, previous slide. And so for these 3, in other words, for these 3 graphs, we know they have, these 3 little graphs, we know they have the right frequency. And we want to prove that for every f, f has the right frequency. So again, we look at a tiny little piece of this matrix for k equals 1. And notice that we have equality here. This times this is equal to this times this. So in other words, this submatrix here is singular. This means that these 2 columns must be linearly dependent, because this is a positive semi-definite matrix. So if there's a diagonal submatrix which is singular, then the whole columns must be dependent. And in fact, I mean, the dependence is, by looking at these numbers, is that this column is P times this column. But then, for example, I can take, this means any star with any number of branches. I get here 1 more branch if I glue this on. So it follows that if I increase the size of the star by 1, I increase this f by exactly a factor of p. So numerically, I get that it goes from p to the k by induction to p to the k plus 1. So what I get is that stars satisfy what I want to prove. Okay, let's go on for k equals 2. And I again look at just these 4. And just as before, I know that the conditions imply that I have equality here. That's 1 p squared, p to the 4th. So this is a singular submatrix, so the corresponding columns are singular. So in particular, if I take now this complete bipartite graph with 2 and k points, gluing this on, I get a complete bipartite graph by 2 and k plus 1 points. I get that this is p squared times this. So numerically, I get by induction that for every one of these complete bipartite graphs. The value is p to the 2k, which means that these complete bipartite graphs satisfy what I want. Now, that doesn't look like it's, you know, I mean, there are many, many graphs, much more complicated structure, but from now on, we just do a very simple induction. So let's take, okay, so let's start here. So this is a node V, which I didn't write out the label, so that's node V, and it has k neighbors. So this is the graph for which I want to prove that it has the right density. And by induction, I assume that smaller graphs have the right density. And in fact, this is the one which I obtained by deleting this node. So these two graphs are somewhere in this table. In fact, they are I mean, this will be somewhere it will occur in the first column. I don't glue on anything. And here I have this star with k branches. If I glue it on, I get this graph. But now let's look at the top of this again. So I have these 4 here. And all these, I already know they satisfy the relation. So again, this is 1, no edge. So the value here is 1. And so it's p to the k, p to the k, p to the 2k. So again, this is singular. So the 2 columns are proportional. So this column comes from that column by multiplying by p to the k. So the value here comes from this by multiplying by p to the k, and that's it. Okay, so that's now that's more or less the end of this story about quasi-random graphs. I mean, this proof about quasi-random graphs, and I think I will just say a few words about what are sort of the further plans that I would like to talk tomorrow about. So I want to make further use of this matrix. And so one question is how well do these properties, these basic properties of this matrix capture combinatorial properties of these homomorphism functions or subgraph counts and so on? It seems that you get a lot out of it. I mean, I showed you a few, and you could go on and have other extremal results in graph theory proved just by observing appropriate portion of this matrix. It turns out that, in fact, you can prove essentially a converse to the main lemma. So that will be, I will try to sketch that if you have any graph parameter, that for any graph parameter, you can construct these matrices for every k, except that now in this, let me go back here rather than forward. That's the place. So you evaluate the graph parameter here, and that's what you write there, and you get these matrices. And if these matrices are positive semi-definite and have the right rank, then there exists a graph, so G, so that they actually count homomorphisms into G. So that will be one of the theorems. And the other topic that I would like to talk, 2 more, I don't know how much will fit. A second topic I would like to talk about is that we define this convergence by counting homomorphisms of F into G. So for every G, we looked at all possible Fs, and that was the vector, and then that had to be convergent. Now you can sort of flip the two. And you can ask what happens if you are interested in counting homomorphisms. So you have a sequence of graphs Gn, and you count homomorphisms into some H, and you want to know whether this is convergent. And now it turns out that this is exactly what statistical